Hello everyone, today we'll study dot product. First of all, let me introduce the norm of a vector. Let V be a vector. The length or the magnitude of vector V is called the norm of vector V. So the length, the magnitude, and the norm all mean the same thing. And it's denoted by this symbol here, double bars with a V inside. This symbol means the length, the magnitude, or the norm of a vector V. Next, let me show you how to find the norm of a vector. Look at this example. Let V be the vector in R2. For R2, we can consider R2 as an XY plane. Here, vector V is V1, V2. In XY plane, V1 represents X coordinate, and V2 represents Y coordinate. So vector V is here. How can we draw vector V? Vector V is a vector from the origin to this point. Vector V is a vector from the origin to this point. That's vector V. How can we find the norm of this vector? For the norm of this vector, we can try to use Projection Theorem. If I draw a perpendicular line here, then this side is V1. This side is the same as this side. So this side is V2. Then for the norm of V, we can use Projection Theorem. We know that norm of V equal to square root of V1 squared plus V2 squared. That's how I find the norm of V if V belongs to R2. Next, if V belongs to R3, how can we find the norm of V? Next example, let V equal to V1, V2, V3 in R3. How can we find the norm of V? In R3, there are three axes. The x-axis, the y-axis, and the z-axis. Since V is V1, V2, V3, V1 represents S coordinate, V2 represents Y coordinate, and V3 represents Z coordinate. Assume V1 is here, V2 is here, and V3 is here. Assume those are V1, V2, V3. Next, let's draw the point. First of all, let's find V1, V2 in the XY plane first. Point V1, V2 in the XY plane somewhere here. Find the point V1, V2 in the XY plane first, somewhere here. That's the point V1, V2, 0. In the XY plane, the Z coordinate is 0. Next, raise this point by V3. Let's raise the entire parallelogram for V3 units. This is point V. Then for vector V, we connect the origin to the point. Draw a vector from origin to the point. Draw a vector from origin to the point here. This is vector V. Draw a point from origin to this point. This is vector V. How can we find the norm of this vector? First of all, let's find the norm in the XY plane first. Find the distance in the XY plane first. How can we find this distance here? Assume this side is D. How can we find distance D? For distance D, think of this triangle. This is a right triangle. This is a right triangle in the XY plane. This side is V1. This side is V2. So for D, we can use Projection Theorem. We know that D squared equal to V1 squared plus V2 squared. That's how we find D. Next, consider this triangle. Consider this triangle here. This side is V3. Since I raised this point V3 units, this side is V3. This side is V3. This side is D. And this is a right angle, because this line is perpendicular to the xy plane. This line is perpendicular to the xy plane. This is a right angle. This is a right angle here. Since this is a right angle, we have a right triangle here with three sides: D, V3, and magnitude and the norm of V. Then we can use Pythagorean theorem to find norm of V. We know that norm of V is square root of D squared plus V3 squared. That's norm of V. And then we know that D squared is V1 squared plus V2 squared. V1 squared plus V2 squared plus V3 squared. That's norm of V. So here we can see that if V belongs to R2, the norm of V is V1 squared plus V2 squared, and then take square root. If V belongs to R3, the norm of V is V1 squared plus V2 squared plus V3 squared, and then take square root. Next, based on the previous examples, let me define the norm of a vector in Rn. Let V equal to V1, V2, Vn belong to Rn. The norm of vector V is defined as norm of vector V equal to square root of V1 squared plus V2 squared plus Vn squared. In the previous example, we can see that for V belong to R2, when we try to find the norm, we first of all square each component, add them up, and then take square root. And for V belong to R3, we do the same thing. We first of all square each component, add them up, and then take square root. That's how we find the norm of vector V in R2 and R3. For vector V in Rn, even though we cannot draw the picture, but it makes sense to define the norm of vector V in a similar way. We first of all square each components, add them up, and then take square root. That's how we define the norm of vector V in Rn. Next, let's look at some examples. The U equal to 1, -2, 4, -1 belong to R4. And the V equal to -1, 3, -2, 1, 4 belong to R5. Find the norm of vectors U and V. So, for the norm of vector U, use the formula, we first of all square each components, add them up, and then take square root. I get square root of 1 squared plus -2 squared plus 4 squared plus -1 squared, which is square root of 1 plus 4 plus 16 plus 1. Together is 22 under square root. So I get square root of 22. That's the norm of vector U in R4. And similarly, for the norm of vector V in R5, do the same thing. Take square root of -1 squared plus 3 squared plus -2 squared plus 1 squared plus 4 squared. Together we get 1 plus 9 plus 4 plus 1 plus 16. Altogether we have 1 plus 9 is 10, 4 plus 1 is 5, 15. 15 plus 16 is 31. I get square root of 31. That's the norm of vector V in R5. So here we can see that by the definition of norm, we always take square root for a non-negative number. So the norm is always non-negative. So keep in mind that the norm of a vector is always non-negative, which means it's always greater or equal to 0 for all vector U, for all vector V. The norm is always non-negative for all vector V. Next, Network theorem. Let V be a vector in Rn, then the norm of V is 0, if and only if vector V itself is a 0 vector. Let's prove it. Since the statement here contains if and only if, we need to prove in both directions. Let's first of all prove from left to right. So assume the norm of vector V is 0. We try to prove that vector V itself is a 0 vector. So let V equal to V1, comma V2, comma Vn belong to Rn. Then we know that norm of vector V is square root of V1 square plus V2 square plus Vn square. Since norm of V is 0, then square root of V1 square plus V2 square plus Vn square is 0. If I square both sides, I have V1 square plus V2 square plus Vn square is 0. Since every term here is greater or equal to 0, since every term is non-negative, and their sum is 0, then every term must be 0. Since every term is non-negative and their sum is 0, that means every term must be 0. Since every term is non-negative and their sum is 0, that means every term must be 0. Hence V1 equals 0, V2 equals 0, and Vn equals 0. I take square root here. Take square root. I get V1 equals 0, V2 equals 0, and Vn equals 0. Hence, vector V is 0, 0, 0 is a 0 vector. If every component is 0, vector V is called 0 vector. If every component is 0, vector V is called 0 vector. So let's prove from left to right. Next, let's prove the other direction. Assume V is a 0 vector. We try to prove that the norm of V is 0. Let V equal to 0, 0, 0 belong to Rn. Then the norm of V is square root of 0 square plus 0 square plus 0 square. There are n terms. The sum of n zeros is 0. Square root of 0 is 0. So the norm of V is 0. Let's complete the proof. The norm of V is 0, if and only if V itself is a 0 vector. Next theorem. Let V be a vector in Rn, and let K be a scalar. Then the norm of Kv is always absolute value of K times the norm of vector V. How can we prove it? First of all, let V equal to V1, V2, Vn belong to Rn. Then Kv is Kv1, Kv2, Kvn. For Kv, I distribute K to each component in vector V. Then the norm of vector Kv is square root of Kv1 square plus Kv2 square plus Kvn square. That can be written as square root of k squared v1 squared plus k squared v2 squared plus k squared vn squared. Then, since k squared is a perfect square, I can pull it out. I get k squared times v1 squared plus v2 squared plus vn squared. Then I can split the square root like this. Square root of k squared times square root of v1 squared plus v2 squared plus vn squared. So here we can see that square root of k squared is absolute value of k, and that's norm of vector v. This is norm of vector v. Let's complete the proof. Next, let me introduce unit vector. Let v be a vector in Rn. If the norm of vector v is 1, then v is called unit vector. So, unit vector is a vector whose norm is 1. Next, let's look at a theorem. Let v be a vector in Rn with v not equal to 0, which means v is not a 0 vector. And let vector u be defined as v divided by norm of v. Then, u is always a unit vector. How can we prove it? First of all, we know that v is not a 0 vector. Then the norm of v cannot be 0. We try to prove that u is a unit vector. That means we try to prove the norm of u equal to 1. What's the norm of u? U is the vector v over norm of v. This expression v over norm of v can be written as 1 over norm of v times vector v. Since norm of v is not 0, 1 over a non-zero number is a scalar. 1 divided by a non-zero constant is a scalar. According to the previous theorem, when we have a scalar times a vector, I can always pull out a scalar and add absolute value. When we have a scalar times a vector, we can always pull out a scalar and add absolute value. Since 1 over norm of v is a scalar, I can pull it outside and add absolute value. Single bar means absolute value. Double bar means the norm of a vector. So I can pull out this scalar and absolute value. If I pull out a scalar, what's left is vector v. If I pull out a scalar, what's left is vector v. Now, inside the absolute value, we have 1 over the norm of v. We know that norm of v is non-negative. Also, number 1 is non-negative. Non-negative number divided by non-negative number is always non-negative. And absolute value of non-negative number is non-negative. It stays the same. Absolute value of non-negative number stays the same. So I get 1 over norm of v times norm of v. Since absolute value of positive number stays the same. And then norm of v can cancel. If I cancel norm of v, I get 1. So norm of u is 1. If norm of u is 1, we say u is a unit vector. Let's complete the proof of this theorem. Note, in the above theorem, the calculation v divided by norm of v is called the normalization of vector v. Let's call the normalization of vector v. Because it always it always generates the unit vector in the same direction of vector v. Because it always generates the unit vector in the same direction of vector v. This calculation, v over norm v is called the normalization of vector v, because it always generates the unit vector in the same direction of vector v. Next, let's create an example. Let u be a vector in R4 and let v be a vector in R5. Normalize vectors u and v. In order to normalize vectors u and v, let's find the norm for vector u first. Norm of vector u is square root of -1 square plus 1 square plus 3 square plus 2 square, which is square root of 1 plus 1 plus 9 plus 4. That's square root of 15. That's norm of vector u. Next, take vector u divided by its norm. Vector u is the vector -1, 1, 3, 2. Its norm is square root of 15. So take each component, divide by square root of 15. I get -1 over square root of 15, 1 over square root of 15, 3 over square root of 15, and 2 over square root of 15. This is a unit vector in the same direction of vector u. Next, let's find the norm of vector v. For norm of vector v, take square root of 2 square plus -1 square plus -2 square plus 4 square plus -3 square, which is square root of 4 plus 1 plus 4 plus 16 plus 9, which is square root of 34. So, in order to normalize vector v, take vector v divided by its norm. Vector v is 2, -1, -2, 4, and -3. Divide by its norm. When we take a vector divided by a scalar, take each component of the vector divided by the same scalar. We get 2 over square root of 34, -1 over square root of 34, -2 over square root of 34, 4 over square root of 34, and -3 over square root of 34. That's the unit vector in the same direction of vector v. Next, let me show you some standard unit vectors. In R is a real line, which is one-dimensional. So it has one standard unit vector called E1. E1 is number 1. In real line, the origin is here. Number 1 is here. That's the vector E1. That's the vector E1 in R. In R2 is two-dimensional. It's a plane. So it has two standard unit vectors. E1 equal to 1, 0. E2 equal to 0, 1. So for R2, consider this is a SY plane. It has two unit vectors. Origin is here. That's the vector 1, 0. This is vector E1. 0, 1 is here. That's the vector E2. They are called the standard unit vectors in R2. In R3 is three-dimensional. So we have three standard unit vectors. E1 equal to 1, 0, 0. E2 equal to 0, 1, 0. E3 equal to 0, 0, 1. In R3, there are 3 axes. Vector 1, 0, 0 is here. That's E1. This vector is E1. Vector 0, 1, 0 is here. That's E2. Vector 0, 0, 1 is here. That's vector E3. So they are the standard unit vectors in R3. In general, in R2, we use I, vector I represent E1, and we use vector J represent E2. In general, in R2, we use vector I represent E1, vector J represent E2. And in R3, we use vector I represent E1. I in R3 is 1, 0, 0. J in R3 is 0, 1, 0. And we use K to represent E3 in R3. Vector K is 0, 0, 1. So I and J in R2 is 1, 0, 0, 1. They are the standard unit vector in R2. I, J, K. They are the standard unit vector in R3. In R3, I is 1, 0, 0. J is 0, 1, 0. K is 0, 0, 1. And in R4, we can draw a picture, but we know that R4 is 4-dimensional. R4 is 4-dimensional. So there are 4 standard unit vectors. E1 is 1, 0, 0. 1, 0, 0, 0. E2 is 0, 1, 0, 0. E3 is 0, 0, 1, 0. E4 is 0, 0, 0, 1. For R4, we don't use IJK to represent the standard unit vectors. We only use E1, E2, E3, E4 to represent the standard unit vectors. And similarly, in R5, R4 is 5-dimensional, so there are 5 standard unit vectors. E1 is 1, 0, 0, 0. E2 is 0, 1, 0, 0, 0. E3 is 0, 0, 1, 0, 0. E4 is 0, 0, 0, 1. E5 is 0, 0, 0, 0, 1. Those are the standard unit vectors in R5. And similarly, in R6, R7, R8, we define the standard unit vector in a similar way. Only for R2, we use I and J to represent the standard unit vectors. And in R3, we use I, J, and K to represent the standard unit vectors. Note, according to the earlier section, we know that the standard unit vector, they are also called the standard basic vectors. The standard unit vectors in Rn is also called the standard basis vectors. So according to the earlier session, we know that the standard unit vectors in Rn is also called the standard basis vectors in Rn. Next, let me show you how to find distance between vectors. Let U and V be vectors in Rn. The distance between vectors U and V is defined as distance from U to V is the norm of the vectors U minus V. That's how we define distance between vectors. How does this definition make sense? Think of this. In R2 or R3, we can draw vectors u and v. In R2 or R3, we can draw vectors u and v. How do we find distance between these two vectors, u and v? In order to find distance between u and v, first step, we shift their tails to the origin. First step, we shift their tails to the origin. Suppose that's the origin. For both vector u and v, we shift their tails to the origin. Once I shift their tail to the origin, then the head, the point on the head has exactly the same coordinate as vector u. And the point and the head here has exactly the same coordinate as vector v. Then, for distance between these two vectors, we measure the distance between their heads. For distance between these two vectors, we measure the distance between their heads. How do we find distance between two vectors? How do we find distance between two points? If I connect 2 points, we can make a vector, either from u to v or from v to u. Here we have u minus v, head minus tail. If I consider that's a vector from u to v, that's the head, that's the tail. So u is the head, v is the tail. Vector u minus v represents this vector. This vector is u minus v, head minus tail. And the norm of this vector is the same as the distance from point u to v. The norm of this vector is the same as the distance from point u to v. That's how it makes sense in R2 and R3. Similarly, for higher dimensional space, we can draw the picture, but we define the norm, but we define the distance in the same way. For higher dimensional space, we can draw the picture, but we define the distance in the same way. Distance between vectors u and v is the norm of the vectors u minus v. Next, let's look at some examples. Let u equal to 1, 2, 2, 3, and v equal to 4, -1, 1, 1. Be vectors in R4. Let u and v be vectors in R4. Find distance from u to v. Find distance from u to v. So by definition, for distance from u to v, we find the norm of vectors u minus v. We find the norm of the vectors u minus v. When we subtract two vectors, we subtract their coordinates. 1 minus 4 is -3. 2 minus -1 is +3. 2 minus 1 is 1. 3 minus 1 is 2. That's the vector u minus v. Next, find the norm of this vector. That's the distance between u and v. So for the norm of this vector, we take square root of -3 squared plus 3 squared plus 1 squared plus 2 squared, which is 9 plus 9 plus 1 plus 4. That's square root of 23. That's the distance between vectors u and v. Another example, let u be the vector 2, -1, 0 to 1. And let v be the vector 1, 2, 1, 3, 4. Let u and v be vectors in R5. Find the distance between vectors u and v. So for distance between vectors u and v, that's the norm of the vector u minus v. So for the vector u minus v, we subtract the corresponding components. 2 minus 1 is 1. Negative 1 minus 2 is negative 3. 0 minus 1 is negative 1. 2 minus 3 is negative 1. 1 minus 4 is negative 3. Next, we find the norm of this vector. That's square root of 1 square plus negative 3 square plus negative 1 square plus negative 1 square plus negative 3 square, which is square root of 1 plus 9 plus 1 plus 1 plus 9. Altogether, we have square root of 21. That's the distance between the vectors u and v. Next, let me introduce dot product. Let u and v be vectors in Rn. The dot product of vectors u and v is defined as u dot v equal to u1 times v1 plus u2 times v2 plus un times vn. So, for dot product of vectors u and v, we multiply the corresponding components and then add them up. That's how we define dot products between two vectors. Next, let's look at some simple examples. Let u be the vector 1, 2, 2, 3, and let v be the vector 4, negative 1, 1. Let u and v be vectors in R4. Find the dot product u dot v. So for the dot product u dot v, we multiply the corresponding components and then add them up. First component 1 times 4 is 4. Second component 2 times negative 1 is negative 2. The third component 2 times 1 is 2. And the fourth component 3 times 1 is 3. Multiply the corresponding components and then add them up. We get 7. So that's the dot product u dot v. Another example. Let u be the vector 2, negative 1, 0, 2, 1. And let v be the vector 1, 2, 1, 3, 4. Let u and v be vectors in R5. Find the dot product u dot v. So for u dot v, from the dot product u dot v, multiply the corresponding components and then add them up. 2 times 1 is 2. Negative 1 times 2 is negative 2. 0 times 1 is 0. 2 times 3 is 6. 1 times 4 is 4. And then adding up, we get 10. That's the dot product of these two vectors. Note, keep it in mind. For vectors u and v, in Rn, the dot product u dot v is always a real number. For u and v in Rn, the dot product u dot v is always a real number. Next, let me show you some properties of dot product. Let u, v, w be vectors in Rn, and let k be a scalar. First property says u dot u is always the norm of u squared. Second property says u dot v equal to v dot u. If I switch order, the dot product stays the same. The third property says u dot v plus w is the same as u dot v plus u dot w. It's the same as I distribute u to both of them. Okay, u dot v plus u dot w. Same thing for the right distribution. I can distribute w to u and w to v. I get u dot w plus v dot w. Next property, when we have a scalar k times the dot product, it's the same as k times u dot v or u dot k times v. When we have a scalar times the dot product, I can multiply the scalar to one of the vector first, and then take dot product. Answer is the same. The next property says 0 vector dot u is always 0, and u dot 0 vector is also 0. Let's prove it. For the first property, we try to prove that u dot u is the norm of u squared. So let u equal to u1, u2, un belong to Rn. We try to prove that the left side equal to the right side. The left side is u dot u. So for dot product, we multiply the corresponding components and then add them up. First component is u1, so you get u1 times u1. Second component is u2, so you get u2 times u2. And the last component is un, so you get un times un, which is un squared. That's the left side, u dot u. For the right side, we know that the norm of u is square root of u1 squared plus u2 squared plus un squared. So the norm of u squared, square cancel square root. That's u1 squared plus u2 squared plus un squared, which equal to u dot u. So let's prove the first statement. The proof for the rest is similar. We set our general vectors u, v, w in Rn, and then show that left side equal to the right side. I leave the rest for you. Next, let's create an example. Let u and v be vectors in Rn. Assume the norm of vector u is radical 3. The norm of vector v is radical 5. And the dot product u dot v is 2. Find the norm of the vector u plus 3v. And the distance between the vectors 2u and v. Now, first example here. How do we find the norm of the vector u plus 3v? We know that by the first property of dot product, the norm of a vector square is the dot product, the vector dot itself. If we apply it here, I can first of all square the norm. Then, by the first property of dot product, this can be written as u plus 3v dot itself, u plus 3v, by the first property of dot product. Next, I can distribute. By the third property, I can distribute. If I distribute, I get u dot u. If I distribute, I get u dot u plus u dot 3v plus 3v dot u plus 3v dot 3v. Then, by the fourth property, if there's a scalar times a vector, in dot product, if there's a scalar times a vector, we can pull out the scalar. If there's a scalar times a vector in a dot product, we can always pull out the scalar, right? As a scalar times the dot product of the vectors. So by the fourth property, u dot 3v, I can write it as 3 times u dot v. And 3v dot u, I can write it as 3 times v dot u, polar scalar. Here, 3v dot 3v, I can pull out both 3. I get 9 times v dot v. Sorry, this is u. This is 3 times u dot v. Pull out 3 from each of them, I get 9 times v dot v. And we know that by the first property, u dot u is the norm of u squared. By the second property, we know that u dot v is the same as v dot u. So here, u dot v and v dot u, they are exactly the same. We get 3u dot v plus 3v dot u. That's the same as 6u dot v. Since they are exactly the same, I can combine like terms. I get 6 times u dot v plus 9 times v dot v. And by the first property, we know that v dot v is the norm of v squared. Then plugging numbers. Norm of u is radical 3. The dot product u dot v is 2. Norm of v is radical 5. Radical 3 squared is 3. 6 times 2 is 12. Radical 5 squared is 5. 5 times 9 is 45. 3 plus 12 is 15. 15 plus 45 is 60. So the norm of u plus 3v squared is 60, which means the norm of u plus 3v is square root of 60. Square root of 60 can be rewritten as 2 square root of 15. That's the norm of the vector u plus 3v. Next, how about distance from 2u to v? How about distance from 2u to v? The distance from 2u to v is the norm of the vector 2u minus v. So same procedure. We can square the norm first and then take square root in the end. If I square the norm, I get 2u minus v. Norm of 2u minus v squared. By the first property of dot product, I can write this as 2u minus v dot 2u minus v. Then by distribute property, I have 2u dot 2u plus 2u dot negative v plus negative v dot 2u plus negative v dot negative v. Then I can pull out scalar. When we have a dot product, if there's a scalar, I can pull out scalar. If I pull out 2 here, pull out 2 here, I get 4 times u dot u. If I pull out 2, pull out negative 1, I get negative 2 times u dot v. If I pull out negative 1, pull out 2, I get negative 2 times v dot u. If I pull out negative 1, pull out negative 1, I get positive 1 times v dot v. And we know that the dot product u dot u is the norm of vector u squared. The dot product u dot v and v dot u, they are exactly the same. So I can combine like term here. I get negative 4 times u dot v. And the dot product v dot v is the norm of vector v squared. Then plug in. Norm of u is radical 3. The dot product u dot v is 2. V squared. Norm of v is 5. Norm of v is radical 5, so I get radical 5 squared. Here, radical 3 squared is 3. 3 times 4 is 12. 4 times 2 is 8. Radical 5 squared is 5. Then 12 minus 8 plus 5 is 9. That's the square of the norm 2u minus v. So the distance from 2u to v is the norm of 2u minus v. Here we take square root. Square root of 9 equal to 3. That's the distance between the vectors 2u and v. Next, let me introduce the Cauchy-Schwarz inequality. Let u and v be vectors in Rn. Then the absolute value of the dot product u dot v is always less or equal to the norm of u times norm of v. This is always true for all vectors. Next, let's look at some examples. Let u be the vector 2, 1, negative 1, 3. And let v be the vector negative 4, 2, 3, negative 2. Let u and v be vectors in R4. Show that it satisfies the Cauchy-Schwarz inequality. Then the absolute value of the dot product u dot v is less or equal to the norm of u times norm of v. So let's first of all find the dot product. For the dot product u dot v, we multiply the corresponding components and add them up. 2 times negative 4 is negative 8. 1 times 2 is 2. Negative 1 times 3 is negative 3. 3 times negative 2 is negative 6. Add them up. Negative 8 plus 2 is negative 6. Negative 6 minus 3 is negative 9. Negative 9 minus 6 is negative 15. If I take absolute value of u dot v is absolute value of negative 15, which is positive 15. Next, find the norm for vector u and v. The norm of vector u is square root of 2 square plus 1 square plus negative 1 square plus 3 square, which is square root of 4 plus 1 plus 1 plus 9. That's square root of 15. Next, for the norm of vector v, we take square root of negative 4 square plus 2 square plus 3 square plus negative 2 square. Together we have 16 plus 4 plus 9 plus 4. 16 plus 4 is 20. 20 plus 9 is 29. 29 plus 3 is 33. So I get square root of 33. Then we multiply the norm. Norm of u times norm of v. I get square root of 15 times square root of 33. That's square root of 495. If I use my calculator, I get 22.25. So here we can see that the absolute value of the dot product is less or equal to the norm of u times norm of v. 15 is less than 22.25. Next, let me introduce the triangle inequality. Let u, v, w be vectors in Rn. Then the norm of vectors u plus v is less than or equal to norm of u plus norm of v. The picture looks like this. Suppose that's vector u. Suppose that's vector v. If I connect the initial tail to the final head, that's the vector u plus v. Here you can see that the norm of vector u plus v is shorter than the norm of u plus norm of v, because between 2 points, a straight line is the shortest distance. So the norm of u plus v is less than the norm of u plus norm of v. That's the first triangle inequality. Second triangle inequality says distance from u to v is less than distance from u to w plus distance from w to v. So for second statement, think of u and v as points. In Rn, we can consider every vector as a point. If I shift the tail of the vector to the origin, we can consider each vector as a point. For second statement, consider u is here, point v is here, and point w is here. Distance from u to v, that's the distance from u to v, is less or equal to distance from u to w. This side is the distance from u to w, plus distance from w to v. This side is the distance from w to v. So we know that between 2 points, straight line is the shortest distance. Between 2 points, the straight line is the shortest distance. So this distance from u to v is shorter than distance from u to w plus distance from w to u. This side is less than the sum of these two sides. That's called triangle inequality. Next, let's prove these two statements. For the first statement, we try to prove that the norm of u plus v is less than or equal to the norm of u plus the norm of v. If we try to prove it directly, it may be too complicated. So a better way is that we can try to square both sides and then compare their squares. Since both sides are positive, the larger square, the larger it is. So for the first statement, let's square both sides. If I square left side, I get the norm of u plus v squared. If I square the right side, I get the norm of u plus norm of v squared. So let's compare their squares. Since both sides are positive, the norm is always positive. Since both sides are positive, the larger square, the larger it is. So on the left side, the norm of u plus v squared can be written as u plus v dot u plus v. Then by distribution law, we have u dot u plus u dot v plus v dot u plus v dot v. And we know that u dot u is norm of u squared. U dot v is the same as v dot u, so that's twice u dot v. And v dot v is the norm of v squared. That's the left side. Now for the right side, let's expand the perfect square. I get the norm of u squared. Those are real numbers, so I can expand the perfect square. Norm of u squared plus twice norm of u times norm of v plus norm of v squared. Then if we compare left side and right side, we can see that the first term looks exactly the same. The last term looks exactly the same. The only difference is the middle term here. Here, since the dot product u dot v is less than or equal to absolute value of u dot v, and by Cauchy's law inequality, absolute value of u dot v is less or equal to the norm of u times norm of v, then we can say that twice u dot v is less or equal to twice norm of u dot norm of v. Since the first term and the last term looks exactly the same, and the middle term is smaller, then left side is less than the right side. So norm of u plus v squared is less or equal to norm of u plus norm of v squared. Then if I take square root on both sides, norm of u plus v is less or equal to norm of u plus norm of v. That's the first statement. norm of u plus v is less or equal to norm of u plus norm of v. Now, for the second statement, we try to prove that distance from u to v is less or equal to distance from u to w plus distance from w to v. We know that distance from u to v is the norm of vector u minus v. The norm of vector u minus v can be written as norm of u minus w plus w minus v. I can add and subtract w in the middle. This can be written as norm of u minus w plus w minus v. Then we have two vectors here. We have two vectors inside the norm. By the first triangle inequality, this is less or equal to norm of u minus w plus norm of w minus v. When we have two vectors inside the norm of u plus v is less or equal to norm of u plus norm of v. We consider this is the first vector, and this is the second vector. By the first triangle inequality, I get this. And this is the distance from u to w. Norm of u minus w is the distance from vector u to vector w. Norm of vector w minus vector v. That's the distance from w to v. Let's complete the proof for the second statement. Next, let's look at a theorem. Let u and v be vectors in R2 or R3. And let's set up an angle between the vectors u and v. Then the dot product u dot v is the same as norm of u times norm of v times cosine theta. How can we prove this theorem? First of all, let me remind you the law of cosine. Law of cosine says, suppose we have a triangle ABC. If the angle opposite to side C is theta, then we have C squared equal to A squared plus B squared minus 2AB times cosine theta. Here theta is the angle opposite to side C. This is called the law of cosine. We will prove this theorem based on law of cosine. We know that for u and v in R2 or R3, we can draw the vector u and v. Assume that's vector u, that's vector v. First step, in order to form a triangle, we shift their tails together. In order to form a triangle, we shift their tails together. So for vector u and v, we shift their tails together. Shift the tail of vector u and v together. Next, try to form a triangle. We know that this side is norm of v. This side is norm of v. This side is norm of u. That's an angle between the vectors. That's angle theta. Theta is the angle between vectors u and v. How about this side? What's this side here? We don't know what it is. Let's call this side x. Then what's x? Assume x is this vector. What's vector x? Based on the picture, we know that vector v plus x equal to vector u. Based on the picture, we know that vector v plus vector x equal to vector u. V plus x equal to u. Then if I solve the equation for x, subtract v from both sides. S equal to u minus v. So here x is the vector u minus v. So this x is the vector u minus v. So this side is the vector u minus v. Then by law of cosine, we know that the norm of this side u minus v squared equal to the norm of u squared. Here, norm of u represents A, norm of v represents B, norm of u minus v represents C. Norm of u plus norm of v, norm of u squared plus norm of v squared minus 2 times norm of u times norm of v times cosine theta. By law of cosine, we have this equation. Next, let's try to simplify the left side and the right side. On the left side, we have u minus v, the square of the norm of u minus v. By the first property of dot product, this can be rewritten as the dot product u minus v times u minus v. If I distribute, I get u dot u minus plus u dot negative v plus negative v dot u plus negative v dot negative v. Then I can pull on a coefficient. If there's a scalar in front of vector, I can pull on a scalar, pull on negative 1. I get negative u dot v. Pull out negative sign, I get negative v dot u. Pull out both negative sign. Double negative is positive. We get v dot v here. And then we know that the dot product u dot u is the norm of u squared. The dot product u dot v and v dot u, they are exactly the same. So we get minus 2u dot v. And the dot product v dot v is the norm of v squared. That's the left side. That's the left side. Equal to the right side. Let's keep the right side the same. Right side is norm of u squared plus norm of v squared minus 2 times norm of u times norm of v times cosine theta. I can cancel norm of u squared from both sides. Cancel norm of v squared from both sides. What's left is negative 2 times u dot v equal to negative 2 times norm of u times norm of v times cosine theta. Next, I can divide both sides by negative 2. So I get u dot v equal to the norm of u times norm of v times cosine theta. That's exactly the same as what we have here. So let's complete the proof for this theorem. Note, the previous theorem can always be written as cosine theta equal to the dot product u dot v over norm of u times norm of v. In the previous theorem, if I divide both sides by norm of u times norm of v, I get cosine theta by itself. If I divide both sides by this, I get cosine by itself. So I get cosine theta equal to the dot product u dot v over norm of u times norm of v. That's what we have here. If I apply inverse cosine on both sides, I get theta equal to inverse cosine of u dot v over norm of u times norm of v. So we can always use the above formula to find the angle between vectors u and v. If u and v are vectors in R2 or R3, we can always use this formula to find angle between the vectors u and v. Also, based on the function y equal to inverse cosine of x, the graph looks like this. That's the graph of the function y equal to inverse cosine of x. In this function here, we know that if x is positive, theta, angle theta is between 0 and pi over 2. If x is positive, angle theta is between 0 and pi over 2, which means between 0 and 90 degrees. If x is negative, then angle theta is between pi over 2 and pi, which means the angle is between 90 and 180. And we know that if the dot product u dot v is positive, since the norm of both u and v are positive number over positive number must be positive. So if the dot product u dot v is positive, then x must be positive. So angle theta is a cube angle. That means angle theta is between 0 and 90 degrees. If the dot product u dot v is greater than 0, it's positive, then angle theta, the angle between the two vectors u and v, must be a Q angle, which means angle theta is between 0 and 90 degrees. However, if the dot product u dot v is negative, since the denominator is always positive, negative number divided by positive number is negative. If angle theta is, if x is negative, angle theta is between 90 and 180, then it's an obtuse angle. Obtuse angle means angle is between 90 and 180 degrees. So if the dot product u dot v is greater than 0, theta is a Q angle. It's between 0 and 90. If the dot product u dot v is less than 0, then the angle theta is always an obtuse angle, which means angle theta is between 90 and 180. So keep in mind that the angle between two vectors is always between 0 and 180. The angle between two vectors is always between 0 and 180. Or if we have angle more than 180, and in this case, we choose the smaller angle. This angle is less than this angle, so we choose this angle to be the angle between vectors u and v. So always, angle between two vectors is always between 0 and 180. If the angle is more than 180, use the smaller angle. Use the smaller angle here. That's the angle between vectors u and v. So we know that for vectors in R2 or R3, we can always use this formula to find angles between the vectors. However, what if we have vectors in higher dimensional space? Then how can we find angles between the vectors for vectors in higher dimensional space? Let's think of this. Let u and v be vectors in Rn. Then, by Cauchy-Schwarz inequality, we know that absolute value of u dot v is always less or equal to the norm of u times norm of v. If an absolute value is less than some positive number, if the absolute value is less than some positive number, that means what's inside must be between negative number, negative a, and positive a. Assume a is positive. If an absolute value is less than some positive number, what's inside is between negative a and positive a. So same thing here. If an absolute value is less than some positive number, what's inside? U dot v must be between negative u, norm of u times norm of v, and positive norm of u times positive norm of v. Or if I divide all three parts by norm of u and norm of v, or if I divide all three parts by norm of u times norm of v, I have negative 1 is between the dot product u dot v over norm of u times norm of v is less or equal to positive 1 if I divide all three parts by norm of u times norm of v. I get u dot v, the dot product u dot v over norm of u times norm of v is between negative 1 and 1. So for vectors in higher dimensional space, if I define angle theta to be inverse cosine of u dot v over norm of u times norm of v, this is well defined because what we input is a number between negative 1 and 1. For inverse cosine function, if I input a number between negative 1 and 1, I can get an angle between 0 and 180. So if I define angle theta in this way, this is well defined. This is well defined for u and v in higher dimensional space. So since this formula works for vectors in R2 or R3, and it's also well defined for all vectors in higher dimensional space, so it makes sense to define an angle in higher dimensional space in this way. So for angle between vectors, we define angle between vectors in this way, since this formula works for angles in R2 and R3, and also is well defined for all vectors in higher dimensional space. So it makes sense to define angle in this way. So let me define angle of vectors. Let U and V be vectors in Rn. The angle between vectors U and V is defined as angle theta equal to inverse cosine of U dot V over ln of U times ln of V. That's how we define angles for vectors in higher dimensional space. So based on this formula, based on this definition here, this formula is equivalent to this formula. So this formula here, U dot V equal to ln of U times ln of V times cosine theta. This is true for all vectors in Rn, not only R2 and R3, it works for all vectors in Rn. So according to the above definition, of angle, in Rn, the formula U dot V equal to ln of U times ln of V times cosine theta is true for all vectors in Rn. Not only R2 and R3, it's true for all vectors in Rn. Next, based on the definition of an angle of vectors, let me define parallel and perpendicular vectors. Before I formally define what it is, let's look at some examples first. Let U and V be non-zero vectors. Let K be a scalar. If U equal to KV, then what's the angle between U and V? What's the angle between U and V? By the definition of angle, we know that cosine theta is always the dot product U dot V over ln of U times ln of V. Here, since U is KV, so we get KV dot V over the ln of KV times ln of V. Then in the numerator, for KV dot V, K is a scalar. I can pull out a scalar, write V dot V. In the denominator, we have ln of KV times ln of V. Since K is a scalar, I can pull out K. Since K is a scalar, I can pull out K. If I pull out K, I got absolute value of K times ln of V times another ln of V. And we know that in the numerator, the dot product v dot v is the norm of v squared. In the denominator, norm of v times norm of v is also norm of v squared. So you get absolute value of k times norm of v squared. In the numerator and denominator, norm of v can cancel. We get k over absolute value of k. So here, if k is positive, then k is the same as absolute value of k. I get positive 1. If k is negative, negative number over positive number is negative. We get negative 1. So k over absolute value of k is either positive or negative 1, which means cosine theta is either positive 1 or negative 1. If cosine theta is 1, then what's theta? We know that for inverse cosine function, inverse cosine of 0 is 1. Inverse cosine of 0 is 1. So if cosine theta is 1, theta is 0 degree. Or if cosine theta is negative 1, in the inverse cosine function, inverse cosine of negative 1 is pi, which is 180. For two vectors, if an angle between two vectors is 0 degree, that means two vectors, they point to the same direction. If angle between two vectors is 0 degree, that means these two vectors, they point to the same direction. If an angle between two vectors is 180 degree, that means these two vectors, they point in the opposite direction. In both cases, they are parallel vectors. In both cases, they are parallel vectors. So, it makes sense to define parallel vectors in the following way. Let u and v be vectors in Rn. If u equal to kv for some scalar k, then we say vectors u and v are parallel. Denoted by u parallel to v. If u equal to kv for some scalar k, then we say vector u and v are parallel vectors, denoted by u parallel to v. Note, by this definition, the zero vector the zero vector 0 is parallel to every vector. The zero vector 0 is parallel to every vector because zero vector can always be written as scalar 0 times every vector v. Here, this 0 is a scalar. This is a zero vector. Zero vector can be written as the scalar 0 times every vector. So zero vector is parallel to every vector. Keep in mind that zero vector is parallel to every vector by this definition. Zero vector is parallel to every vector. Next, let's look at another example. Let u and v be non-zero vectors. If the dot product u dot v is 0, then what's the angle between vector u and v? If the dot product u dot v is 0, then what's the angle between vectors u and v? We know that the angle between vector u and v, cosine theta, is the dot product u dot v over the norm of u times the norm of v. Since u and v, they are non-zero vectors, denominator is not 0, but numerator is 0. 0 over a non-zero number is always 0. If cosine theta is 0, what's theta? If cosine theta is 0, what's theta? We know that inverse cosine of 0 is pi over 2. Inverse cosine of 0 is pi over 2. So cosine of 90 degrees is 0. Since inverse cosine of 0 is pi over 2, then when cosine theta is 0, theta must be a 90-degree angle, which means they are perpendicular. If an angle between two vectors is 90 degrees, that means two vectors perpendicular. So based on this fact here, let me define the perpendicular vector in the following way. Perpendicular vector is also called orthogonal vector. Let u and v be vectors in Rn. If the dot product u dot v is 0, then we say vectors u and v are orthogonal. Orthogonal also means perpendicular. Denoted by u orthogonal to v. So if the dot product of two vectors is 0, we say two vectors orthogonal, denoted by u orthogonal to v. Note, by this definition here, we know that 0 vector dot every vector is 0. Then 0 vector is orthogonal to every vector. The 0 vector is orthogonal to every vector, which means perpendicular to every vector. The 0 vector is perpendicular to every vector. We know that 0 vector dot every vector is always 0. 0 vector dot every vector is always 0. Therefore, 0 vector is orthogonal to every vector. 0 vector is perpendicular to every vector. Next, let's create an example. For each of the following pair of vectors, determine whether they are parallel, orthogonal, or neither. First example, let u and v be vector in R4. Are they parallel? Here we can see that u and v, they are not scalar multiple of each other. So we can say that they are not parallel. Are they perpendicular? Are they orthogonal? Let's check their dot product. 1 times 0 is 0. 2 times 2 is 4. 0 times negative 3 is 0. 4 times negative 1 is negative 4. Adding up, I get 0. If the dot product of two vectors is 0, then they are orthogonal vectors. So we say u is orthogonal to v. Vector u is orthogonal to vector v. Number 2, u and v are vectors in R5. Are they parallel, orthogonal, or neither? Let's observe here. Are they parallel? Let's compare the ratio of each components. For the first component, -4/6 is -2/3. For the second component, 2/3. 2/-3 is also -2/3. For the third component, -6 and 9. -6/9 is also -2/3. The third component, 0, 0. 0 is always a multiple of 0. 8, -12. 8/-12 is also -2/3. Since the ratio of every component is the same, then you can say that U and V, they are scalar multiple of each other. So U equal to, we know that 2/3. U equal to 2/3 times V. U equal to -2/3 times V. Since the ratio of every component is 2/3, -2/3, then we can say U equal to -2/3 times V. If we take -2/3 times V, we get exactly the same vector as vector U. Since U equal to -2/3 times V, we can say that vector U is parallel to vector V. Are they orthogonal? If we check their dot product, -4 times 6 is -24. 2 times -3 is -6. -6 times -9 is -54. 0 times 0 is 0. 8 times -12 is -96. We can see that the answer is negative, which is not 0. So U is not orthogonal to V. Next example. U and V are vectors in R3. Are they parallel, orthogonal, or neither? Let's check the ratio between the vectors first. First component, 3 divided by -1, the ratio is -3. Second component, 2 divided by 1, ratio is 2. The third component, 5 divided by 2, ratio is 5/2. Since the ratio between each component is not the same, we can say that U and V, they are not scalar multiple of each other. So U and V, they are not parallel to each other. U and V are not parallel to each other. Now, are they orthogonal? Let's check their dot product. Are they orthogonal? Let's check their dot product. What's U dot V? 3 times -1 is -3. 2 times 1 is 2. 5 times 2 is 10. Altogether, -3 plus 2 is -1. -1 plus 10 is 9. 9 is not 0. So U is not orthogonal to V. So they are neither parallel nor orthogonal. Next example. U and V, they are vectors in R3. Here U is the 0 vector. Since U is the 0 vector, by definition of parallel and orthogonal vectors, we know that 0 vector is always parallel to every vector, and 0 vector is always orthogonal to every vector. Since U is the 0 vector, in R3, then we know that U is parallel to every vector, and U is orthogonal to every vector. Next, let's observe an example. Let U and A be vectors in R2 or R3. Where A is not 0. A is not 0 vector. Then, for vectors in R2 or R3, I can draw a vector in a 2D paper. Assume that's vector U. Assume that's vector A. Then, there exists W1 and W2. There exist vectors W1 and W2. such that W1 is parallel to U. W1 is parallel to A. W2 is perpendicular to A. And the sum of W1 plus W2 equal to vector U. Then for these two vectors, we can always find vectors W1, W2, such that W1 is parallel to A. And W2 is perpendicular to A, or orthogonal to A. Such that W1 plus W2 is vector U. This is true for all vectors in R2 or R3. And in general, this is also true for all vectors in Rn. This is called the projection theorem. This is called the projection theorem. This theorem is actually true for all vectors in Rn. Let U and A be vectors in Rn. Let U and A be vectors in Rn, where A is not a zero vector. Then there exist vectors unique vectors W1 and W2 such that W1 is parallel to A, W2 is perpendicular to A, and W1 plus W2 equal to vector U. Let's prove it. Since W1 is parallel to A, then we know that W1 is a scalar multiple of A. Here K is a scalar. Since W2 is orthogonal to A, then the dot product W2 dot A must be 0. Also, we know that W1 plus W2 is vector U. That means U equal to W1 plus W2. Here I can replace W1 with KA. So U equal to KA plus W2. Next, I can dot both sides by vector A. I have U dot A equal to KA plus W2 dot A. I can dot both sides by vector A. Dot both sides of the equation by vector A. Then here, I leave the left side the same. I get U dot A equal to the right side. For the right side, I distribute A to the parentheses. I get KA dot A plus W2 dot A. If I distribute A, I get KA dot A plus W2 dot A. Here, KA dot A, K is a scalar. I can pull out scalar like K times A dot A. Since W2 and A, they are orthogonal vectors, W2 dot A is 0. So U dot A equal to K times A dot A. And we know that A dot A, the dot product A dot A is the norm of A squared. Since A is not a zero vector, its norm is not zero, so I can divide both sides by norm of A. If I divide both sides by norm of A, here K is the dot product U dot A over norm of A squared. That's K. Once I know K, I can find W1. So W1 equal to KA, which is U dot A over norm of A squared times vector A. That's W1. And we know that W1 plus W2 is U. So W2 can be written as U minus W1. Since this is W1, so U2 equal to U minus W1. W1 is this. U dot A over norm of A squared times A. Since both vectors U and A are constants, and W1, W2 are written in terms of constants, that means vectors W1, W2 must be constants. Constant vectors must be unique. Therefore, there exists unique vectors W1 and W2 such that W1 is parallel to vector A, W2 is perpendicular, it's orthogonal to vector A, and W1 plus W2 is vector U. That completes the proof. This is called the projection theorem. In this theorem here, W1 is called the orthogonal projection of vector U on A. W1 is called the orthogonal projection of U on A. W1 is called the orthogonal projection of U on A. So keep in mind that in the previous theorem, W1 is called the orthogonal projection of U on A, or the vector component of U along A. Denoted by W1 equal to projection of U on A, which equal to U dot A over norm of A squared times vector A. And W2 is called the vector component of U orthogonal to A. And W2 can be expressed as U minus orthogonal projection of U on A, which is U minus u dot a over norm of a square times vector a. So that's the vector component of u along a. That's the vector component of u orthogonal to a. Next, let's create an example. Let u and a be vectors in R4. Find the vector component of u along a and the vector component of u orthogonal to a. So for the vector component along a, let the projection of u on a, which is u dot a, the dot product u dot a over the norm of a square times vector a. So let's compute the dot product first. Dot product u dot a, we multiply the corresponding components and add them up. -1 times 0 is 0. 2 times 1 is 1. 2 times 1 is 2. 3 times 2 is 6. -2 times -2 is positive 4. Together the dot product is 12. Next, we find norm of a. Norm of a is square root of 0 square plus 1 square plus 2 square plus -2 square, which is square root of 1 plus 4 plus 4, which is square root of 9. Square root of 9 is 3. Then plug in. Projection of u on a is the dot product u dot a over norm of a square times vector a. The dot product u dot a is 12. The norm of a square is 3 square times vector a. A is the vector 0, 1, 2, -2. Here 3 square is 9. 12 over 9 can be written as 4/3. So I got 4/3 times the vector 0, 1, 2, -2. When we have a scalar multiplied to a vector, we distribute the scalar to each component in a vector. That's 0, 4/3. 4/3 times 2 is 8/3. And 4/3 times -2 is -8/3. That's the projection of vector u on a, which is the vector component of u along a. Next, for the vector component of u orthogonal to a, we take u minus the projection of u on a. So take u. U is the vector -1, 2, 3, -2. Minus projection of u along a is this vector. Minus 0, 4/3, 8/3, and -8/3. Let's subtract. -1 minus 0 is -1. 2 minus 4/3 is 2/3. 3 minus 8/3 is 1/3. -2 minus -8/3 is 2/3. That's the vector component of u orthogonal to a. That's the vector component of u along a. That's the vector component of u orthogonal to a.